Can everyone hear me? Yes, good. So hello, and it's fantastic to be back here in person. I think I'm one of the very few people who's been to every Q2B since its inception in 2017, and so it's great to be back here talking to you in person. So I did work for Cambridge Quantum, but as you may have heard, in the past week we've had some big developments. So we have merged with Honeywell Quantum Solutions to form the world's largest and only comprehensive quantum computing company, which is called Quantinuum. And so I've included that. In many of the slides, though, for branding, I haven't had time to update it. So I've actually still kept the Cambridge Quantum, and also to emphasize that because this is our software side of the company, that we really wish to remain hardware agnostic. And so a lot of my slides still have Cambridge Quantum on them. So what I'll be telling you about today is Tket, which is our quantum development platform. And this was one of our first products. We've been working on this for 7 years. To tell you a little bit about our company, at least the Cambridge Quantum side, so we are about 7 years old, and we are based in the UK, as you might have heard. But of course, Quantinuum is really a worldwide company now. And our focus has been on software, and we've had several different verticals within that. What I'll be telling you about today is our compiler and software development kit component of that, but we also work on chemistry and machine learning and natural language processing and cybersecurity. And in fact, in about 30 minutes, our head of cybersecurity, Duncan Jones, will be giving a talk about a new product which was unveiled today called Quantum Origin, which is a commercially available cybersecurity product. And so I encourage you to visit that right after mine if you can. So I think many of you are probably familiar with the reason that we're going to all this effort to develop quantum computing. And that's because quantum computers aren't just a faster computer. They're able to solve problems that we never could have hoped to have solved before. And a prime example is in molecular simulations. If you wanted to attempt to model something like caffeine, my favorite molecule, in principle you could do it, but it would require a computer the size of the entire planet, basically. And if you wanted to simulate molecules just a little bit bigger, it would require a computer the size of the entire universe. So even in principle, we couldn't do that. On the other hand, quantum computers can do that using a very modest number of qubits. And so I'm sure as you hear other talks today, you'll be hearing about the details of how that can be accomplished. The amazing thing is that we actually have quantum computers now. It's not just science fiction, they're actually available. And what's more, there are many paths being developed to building these quantum computers. The power of a quantum computer can be encapsulated in a single metric, which we call the quantum volume. And it's a complicated formula, and I won't go into it here, but basically it allows quantum computers of different technologies and capabilities to be compared. And if you look at the progress in the past few years, it's nothing short of extraordinary. So the blue line shows the progress just made by IBM, and it's quite a bit faster than Moore's law. So this is a logarithmic scale. Notice it's a logarithmic vertical axis here. So it's a straight line, but that's actually exponential progress. And the orange line is the progress made by the Honeywell group, again, now part of Quantinuum, in which they've been able to increase the quantum volume by a factor of 10 each year, and they believe that they can continue with that. So in the next few years, we should see some really extraordinary things coming from quantum hardware. Right now, though, we don't quite have these quantum computers of our dreams. We do have quantum computers, but they're in this what's called Nisk Era. And Nisk stands for Noisy Intermediate Scale Quantum. In fact, I believe this was an acronym coined by John Preskill at the very first Q2B. So I was lucky enough to be there a few years ago when he coined this. So what it means is that we have quantum computers, and they can do things that would be difficult for a normal computer to do, but not quite impossible. We don't have that many qubits. Recently, IBM crossed the 100 qubit threshold. They still have relatively high error rate, and they have some connectivity issues, because oftentimes the qubits aren't coupled as much as we would like. And so a lot of emphasis has gone into what's called hybrid algorithms, where even though we call them a quantum program, a lot of the heavy lifting is still done by classical computing. And so I'm sure in the next few days you'll be hearing about a lot of applications which utilize this hybrid approach to quantum computing. And so that's where we come in. And so I first want to just remind everyone what a compiler is. So just as in traditional computing, a compiler is really a translator between what we as human programmers type, like Python or C or what have you, and what the computer itself executes, because it only executes binary switches and such. And a good compiler doesn't just do this translation, it does it efficiently, because you want your program to use as little memory as possible and run as quickly as possible. And so just as with a traditional compiler, with traditional computers, In the quantum stack, we have something like this. So at the very top of the stack, you have your applications. So these are things that actually do things and solve problems. And those rest on quantum algorithms, which could be things like machine learning or chemistry or NLP or what have you. Those, in turn, depend on the compiler, which in this case is Tket. So Tket is the liaison between the quantum algorithms and the hardware or simulator. Now, right now, we kind of have this embarrassment of riches. We have all these different approaches to quantum computing, and they're a bit idiosyncratic. Each of the different hardware approaches, they have different details, and we have a few different quantum programming languages, like Qiskit or Cirq or Q#. And if you were wanting to move from one platform to the other, it's kind of a hassle, because each of these languages was designed for one platform in mind. Recently, they've been expanding it a bit, but they really were designed with one platform in mind. And we have several different options to choose from right now. And it would be kind of a hassle to move back and forth. And this is precisely why we developed Tket. So Tket is a hardware and language agnostic software development kit. You can program in any of your favorite programming languages, and you can execute your program on any of these platforms. And to show just how universal it is, this is a chart showing some of these different languages that you might use and some of the platforms supporting that. And you see that you're somewhat limited if you chose one of those. But with Tket, you have near universal access. Every major platform and several of the lesser-known platforms are already supported by Tket. And until a few months ago, I said, well, unfortunately, we don't support D-Wave because they use an annealing approach. But of course, as you might have heard, they're moving towards a gate-based approach. And so soon, we expect to be able to support that. And with Quantum Circuits Inc., we expect to soon be able to support that. So really, it is completely universal. Now, how does Tket work? What does it actually do that's so amazing? So as I said, it's universal, so that's great in itself. But the real magic of Tket is that it executes things as efficiently as possible for the platform that you've chosen. So all you have to do is insert one line in your quantum program. You say, I want to execute this on, let's say, the Honeywell H1 system, for example. Tket will do the rest. So Tket knows all the details of that platform, how the qubits are connected, and the error rates and so forth, and it will find the most efficient way to run your program on that platform. So how exactly does it do that? So the first thing it does is it finds a way to make the circuit itself efficient. So this has nothing to do with the hardware. This is just the program itself. And so it does this in two different ways. The first thing it does is what's called people optimization. So it goes through your program and it looks for ways to simplify it just locally using different combinations of gates. So this is a typical quantum circuit that you might have executed. So what it does is it goes through and it looks for combinations of gates. And these are some of the combinations of gates it looks for. So the most obvious one is on the upper left-hand corner there. That's two C0 gates in a row. And as you may know, that's mathematically identical to just nothing, the identity operator, leaving the 2 qubits untouched. So if Tket sees this combination, it just removes those 2 C0 gates, meaning your program runs a little bit faster, and it's a little less likely to make an error. And so these other combinations here, if you had some time on your hands, you could check that each of the substitutions is mathematically identical, but it uses fewer gates, or at least fewer gates that are likely to make an error. And so there is an advantage to this. And I've given the preprint number if you're curious about the mathematics and the details of how it does this type of substitution. So after it does the p-pole optimization, it goes through and it looks for more macroscopic combinations, which is a little bit more difficult to explain here. So again, the first step is just the circuit itself. It has nothing to do with the hardware. But the second step is dependent on the hardware. And so what it does is it takes all of the details of how the physical qubits are arranged and which qubits are coupled to each other, as well as details like the coherence time and the error rates and all of those pieces of information, and it finds the most efficient way to execute your program. Now let me give you an example just to show how important this step is. These are 3 examples of superconducting machines. So they have something in common, but you see the qubits are laid out completely differently, the way that the qubits are coupled here. And what's more, the gates that are native to that architecture are completely different. And of course, these aren't necessarily the gates that you're using in your program. We don't know what gates you're using in your program. So there's 2 different things that Tket has to do. It has to take into account how the qubits are connected and which gates are native. So Tket will do all of that mapping and translation for you. It's completely invisible to you. To give you an example of how important this is, so the architecture here on the left This is an architecture by IBM, and you'll notice that it has at most 4 qubit couplings. So at most, a qubit is talking to 3 others. But the circuit on the right has some 5 qubit couplings. So the 2 qubits on the bottom are talking to each other as well as are coupled to the 3 on top. So naively, we might think there is no way that we could run that program on the right on the hardware on the left. That's not true. We actually can do it. And the way that we do it is using something called routing. So routing just means that we're moving the information between 2 qubits around. And so it's a perfectly legitimate thing to do. You can implement it using just a few CNOT gates. But of course, that's computationally expensive. The whole point was to reduce the gate count, not add to it. So you can move things around, but the cost is that you're adding more gates. So Tket has a built-in optimizer where it quickly figures out what's the optimal path, involving routing possibly, to make this happen so that you can run your circuit on the hardware that you've chosen. Of course, we use Tket for our own internal application development, but we've also made it available for many others. These are just a few of the articles published by other groups, including CERN and IBM and Google, in which they've had very favorable results. They've been using Tket for their own algorithm development and published articles about that. So if you'd like to follow up and read about that later. This was an independent benchmarking done about a year ago by a group called Arlene, and they compared Tket in both gate count and execution time. And you'll see, so on the left is the gate count, and there were far fewer gates required to implement it on different hardware platforms. And on the right, this is the execution time, and I want to point out especially the vertical axis is on a logarithmic scale. So Tket, there in the middle, it wasn't just a little bit faster, it was orders of magnitude faster. And especially in this Nisk era, when running a program efficiently could mean the difference between having it work and having it not work, that's especially important. And so that's why Tket is really important for today's Nisk hardware. As of about 2 months ago, it is completely open source. So even though it is the best compiler and software development kit in the field, about 2 months ago, we made the decision to make it open source, really for the benefit of the whole community. We want everyone to contribute to this. So if you're a hardware group, you can add your own extension so that people can run programs on your machine. And if you're a software developer and you have some clever idea for how to optimize a type of circuit, you can add your own subroutine to the different features. And so again, everything is on GitHub and completely available to the public. Of course, we're always adding to it. There's always new features. Things that we're doing soon. Right now, you download it from GitHub and you run it locally on your machine. But in the future, we're looking to having it be on the cloud. So you would automatically have the latest version, and you would be able to compile using things like Azure or AWS, and it would be easier to collaborate. And we're already starting to look to things like error correction. So beyond the Nisk era, we're already starting to hire out in our team for this. So we'll be ready when the hardware catches up. This is the URL. This is the GitHub repo, if you'd like to take a screenshot there. So again, just download it, and it's a completely standard installation. You just download this, and you use the usual pip install for PyTicket plus whatever module you expect to use, like Qiskit or Cirq or what have you. And that's it. It's completely straightforward and easy to use. Many people use, say, Qiskit or Cirq or what have you, and they just add a line saying, I want to use Tket to compile on such and such hardware. And that's it. So that is it for the general remarks about Tket, but I have a video here made by someone on our Tket team in which they go through an example. So they're going to work through an example in a notebook, exactly how this works. So I will show that here.
Hello, I'm Callum, and I'm here to give a very brief demo of showing how Tket can optimize quantum circuits. So this circuit I have here is a circuit that implements an algorithm known as QAOA, which is a well-known variational quantum algorithm for optimization problems. We can see in this implementation that we have 46 gates, 12 of which are CX or CNOT gates. Now, to actually execute this circuit on a real quantum computer or on a classical emulator, we need to compile this circuit to a gate set that is supported by our chosen device. So we can see that after this compilation, we've converted our gates into SX, RZ, and CX gates, because these are the gates that are supported by this IBM Q emulator that we've chosen here, we can see that this compilation has really substantially increased the gate count in our circuit as well, because we're now up at 80 gates in total, 18 of which are C0 gates. So given the limitations of current quantum computers, especially the fidelities of 2-qubit CX gates, we really want to minimize the number of those 2-qubit gates in order to get the best results we possibly can with today's devices. So one thing we can do is define what's called a noise-aware placement. You can see this noise-aware placement function gives us back a dictionary, assigning each logical qubit in our circuit to a node in our device. This assignment is done with an aim to minimizing the number of 2-qubit operations required to execute our circuit. And this noise-aware placement can actually take into account the noise characteristics of our chosen device as well. The next thing we can do is use what's called a CX mapping pass. A CX mapping pass combines this noise-aware placement with insertion of swap gates to ensure that all our connectivity constraints and routing are satisfied. Now we can see that we're, again, not in the gate set that is supported by our IBM Q emulator backend. So we have to use what's called a rebase to convert the gates back to one that our backend supports. Next, what we can do is use what's called a peephole optimization. A peephole optimization scans the quantum circuit looking for known circuit identities of various kinds with an aim, and spotting redundant operations as well, with an aim to reducing the overall number of gates in our circuit. So we can see that after this optimization, we've really seen a really substantial reduction in our gate count. So we're now at 25 gates, 6 of which are CX gates, which is really great. And you can see as well that our circuit has been converted to CX gates and TK1 gates. This TK1 gate is a parameterized gate which can represent any single qubit rotation. So this combination of TK1 and CX is a universal gate set. Another thing we can do is define what's called a sequence pass, which allows us to compose several compilation passes sequentially. So we can apply our peephole optimization followed by our mapping pass, which takes care of our routing and connectivity. We can then apply our peephole optimizer again to our routing circuit before applying a rebase to get back to a gate set that our backend recognizes. And finally, we can remove any redundant gate operations in our circuit. So if I run this cell, then we end up with 95 gates, 6 of which are CX gates. If I now scroll up and compare this circuit to our default compiled circuit, you can see that this one has 18 CX gates with 80 gates in total. But given how error-prone 2-qubit gates are, this lower number of CX gates is really a huge improvement in terms of executing the circuit to minimize error. So I've really only scratched the surface of what Tket offers in terms of circuit optimization. So I would really encourage you to install Tket yourself and have a look at the manual online. Thank you very much.
Good. And let me just move on here. So these are my contact details. If you have any questions, please feel free to get in touch with me, and I'm happy to answer any questions now, too. Yeah. Yes?
So I have 2 questions. First, you said you are going to implement error correction, but on your slide was written error mitigation.
So right now, there's error mitigation features. In the future, we will do error correction.
Okay.
Correct.
And how do your error mitigation features work?
There are several different approaches. I don't have time to go into them now, but there's several different things that we do. I'm happy to chat with you about that offline.
Okay. And the other question is, you optimize the circuits. They have single qubit rotations with 16 digits precision. So what happens if you have an error which is bigger than 1 in 10 to the 16?
I don't know. I will ask our Tket team about that. It seems like we'd be lucky. If that was the level of the error, 1 part in 16 digits, I would consider myself lucky. But I will ask them about that.
What I think, so it is not going to happen in any known quantum computer for the next probably 100 years.
I will ask our team about that.
Wonderful.
Any other questions?
By the way, for Q&A, we have a mic up here, so if you'd please come up and use the microphone.
So this is, again, to follow up on the question about error correction and fault tolerance. When you move to the new team to do those tasks, will you use this tool?
Sorry, who would we?
When you move to do these new tasks of error correction and fault tolerance, will you be using this tool to help you solve those problems?
Yes, so they would be features that Tket would incorporate. So again, it would be invisible to you as the user. It would just have things that would take care of things like error correction. So we're already hiring people to implement these features, even though today's hardware doesn't quite support it. But we want to be ready in a few years when it does.
Now, that's an answer to a slightly different question. If you're open sourcing this, it usually is in part to encourage contributions from the community.
Yes.
And if you're positioning this as a development platform, then extensions for other people's error correction algorithms become more attractive if the platform is developed with that as a part of the intention. So is there a commitment for these advanced features to provide a stable base to build upon?
A commitment from our company?
From your company.
Absolutely. Oh, yeah. Absolutely. Any other questions? Okay. Thank you again.